Hey, welcome to another episode of Dr. Jordan's World of Math. Today we are going to be talking about graphing the exponential functions. I know 6.1 was a very short introduction to the notation of an exponential function. So we pretty much only dealt with some basic exponential functions like this or like this. So these are the two basic types of exponential functions. It turns out that these are actually the same type. The original, what we call the mother function, f of x equals ax, is the same as f of x equals cax, but in this particular example, c is just 1. So it turns out that these equations are exactly the same function. Typically, in this case, c is not equal to 1. Yeah. Otherwise, if c was equal to 1, I just wouldn't write it. It would be an invisible one. So today we're going to focus on the graphing. So let's graph the function f of x equals 2 to the x power. Or if you prefer, y equals 2 to the x power. It really means the same thing. This is what I call a tomato, and this is what I call tomato. They are exactly the same fruit. We're going to do this much like we did the parabolas and square roots and cubics and things like that. We're going to make a table of the values of the mother function. We're just going to pick a few numbers to get started. If you don't know where to start, then start with a couple negative numbers. I usually like -2, -1. I typically use 0 and then 1 and 2. Okay. The domain, I'll give you a free answer, is -infinity to infinity. So there's your free answer for the homework. Also on the next test, don't forget that. The domain of an exponential function is all real numbers. That essentially means that this function does not violate any of the domain rules. There are no square roots. There are no denominators. You don't have to worry about any restricted values. You can allow x to be anything. Okay. This is what we call a subset of the domain. It's just 5 particular points out of infinitely many choices. You actually already have the y values if you look at your notes from yesterday. I'm going to reproduce them now, but they're exactly the same as they were yesterday. F of -2 is 2 to the -2. Remember this? That's 1/4. Or if you prefer decimal, a quarter. 0.25. I think it's easier to fit it in my box when I use decimals. F of -1 is 2 to the -1, which is 1/2, also known as 0.5. Yeah, that 5 is hard to see. Remember, 0 is a special case. You just get 1. Anything to the 0 power is 1. Technically, it's any non-zero base raised to the 0 power is 1. But in this class, Math 10, we'll keep it. Any number raised to the 0 is 1. Let's do a few more. F of 1, that should be pretty straightforward. That one comes out to be 2. And F of 2 is 4. So this is what we will call the mother function. This is our mother table for f of x equals 2 to the x power. Okay, so let's draw a graph. Got my x and y. when you do your homework, I might ask you for the y value at some point. There's several questions that ask you to evaluate and find the y value. However, on your computer, you probably can't graph the 0.25, but you will be able to graph the 0.5. So you could just start your graphing here with 0.5. All right. That's about as accurate as it'll probably let you go. I might be wrong. You might be able to click on 0.25, but I've tried to get exactly at a quarter. It's pretty difficult. But you can get it at 0.5. That's right about here. Right in the middle between 0 and 1. Okay. And then you can definitely plot the whole numbers. You get 1, 2, and 2, 4. And so let's see what happens here. This is the graph of the function, but there's an interesting behavior down here on the x-axis. As x approaches negative infinity, so x is going towards negative infinity, you can just think of a very big negative number, because you can't actually put infinity into your calculator, all right? But you can put in negative, what's that, 100,000 or something. In fact, you don't even have to go that big. You could probably just do 1,000. That's probably big enough. But you can go as big as you want, as many zeros as you like. A million, a billion, a trillion. And plug it in. Plug a really big number in for x here. And I'm only going to do 1,000 because I don't want to blow up my screen. So I'm going to get 2 to the negative 1,000 power, which is 1 over 2 to the 1,000th power. It is so small, my calculator just says error. It's very, very close to 0, but not actually 0. So this graph is going to keep getting smaller and smaller and smaller and smaller, but it will never actually hit 0. Yeah. One way to think about that is this is never equal to 0. It's always going to be 1 divided by a very big number. And so this is what we call a horizontal asymptote. It's a line that will never get crossed or even touched. Y equals 0. So there's a dotted line on the x-axis. On the Canvas app that I use, it typically comes out in red. So you'll have this red sort of, don't cross me. That's a red line. Don't cross my red line. And as x goes to negative infinity, it's approaching 0. It's getting very close to 0. Okay. You might wonder what's going on over here. As x goes to positive infinity, as you go to the right, as x goes to positive infinity, f of x is just going to get very, very big. Yeah. So this is what we call blows up or blowing up. Yeah, it's like when your phone won't stop dinging. Yeah, your phone is blowing up or something. So it's just going to infinity. You're getting an infinite amount of, dings or text messages or whatever you guys are into these days. Okay, likes or something. I don't know. You can't actually plug in infinity, so you could plug in something really big, like 1,000, positive 1,000. You would get 2 to the 1,000th power, yeah, which is very, very big. It's so big that if I put it into my calculator, I get an error message. Yeah, it says error. But it's actually not an error. It's just more than the memory of this calculator can handle. This calculator doesn't have enough bits to multiply that. It's 2 times 2 times 2 times 2 times 2 times 2, 1,000 times. To give you an idea of how big this actually is, try something like 2 to the 20th power. You don't even have to get very big. 2 to the 20th is already 1,000,000. Yeah. So imagine how big 2 to the 1,000th is. It's way more than 1,000,000. It's more than all the stars in the sky, all the molecules in the universe. It's still more than that. So it's too big. Yeah. So we just say it blows up to infinity. All right, so keep that in mind. That's your mother function. And now we're going to graph functions by using transformations. So by transformations, we are going to graph 2 to the x minus 5. I'm just going to copy this table down so that I can erase it and reuse the space here. So you're going to start with your mother table. All right, the table is based on the base. So this is what we call a base 2 mother table or mother function. Yeah. If I have a different base than 2, then I have to make a new table to start the process. I just made this table 5 minutes ago, so I'm going to go ahead and get some use out of it. Okay. Now remember, from the last couple sections, plus 5, this is going to be a horizontal shift. And remember, it's the opposite. So we're going to go right 5 units, which means we're going to add 5 to all of my x's. Go through the transformation. This is a little technique that I use. If the function is called f, I don't use the letter f until I'm done, and then that reminds me, okay, I'm done. It's now f. Prior to that, it's just y, and now it's f. So those are all my new x's. It's the old x's all shifted to the right 5 units. Notice I did not transform the y values, so they are exactly the same. Okay. And so now watch what happens when I draw my graph. There's my y-axis. There's my x-axis. Let's see, can you see that? Maybe I'll move my x-axis up a little bit. All right, so there's my x-axis. I still have an asymptote at y equals 0. That's what we call the HA, the horizontal asymptote. cannot cross the x-axis. And now I'm going to plot the points. Again, I probably won't plot the 0.25, but I could do, let's see, 1, 2, 3, 4. So I can do 4 and 0.5, about there, 5 and 1, 6 and 2, 7 and 4. And there's your graph. All right. On your Canvas homework, you'll plot 2 of these points. Just any 2 that you like. You don't have to plot the 4 that I did. I like 4 because I can show the curve of the graph. I know it's a little sketchy in here, but I'm doing it by hand. All right, 2 questions that I will ask. What's the domain and what's the range? Domain is free. So please do yourself a favor and memorize that. It's going to be true for quite a while until we get to 6.3 and 4, maybe it'll change. But in 6.1 and 6.2, you get a free answer. The range is not free, so I would not memorize the range. You might be tempted to memorize the range because the answer I'm about to give is a very common answer, but it's not always like that. The range depends on the graph. So you have to draw the graph first and then look at the range. Remember, the range is the y values. All right? It's never going to touch 0, so it's an open interval because it never touches 0, but it blows up to infinity. The y values go up to infinity forever and ever and ever. So the range goes from 0 all the way to infinity, never touching 0, and of course, you never get to touch infinity, at least not in this life. Okay. Try another one? Sure. Graph 3 to the x minus 4. And notice where the minus 4 is this time. Well, last time it was a 5, but was it a 5? Yeah, 5. This time it's outside. So this is a vertical shift. So be very careful. It's the same rules as chapter 3. We were doing all the transformations. The rules haven't changed. So anything on the outside is up and down, vertical. Anything inside or inside the exponent, that's what we call the inside now. This is the exponent is the inside. That would be left and right. Anything on the outside would be up and down. So this is going to be down 4 units. Now, we can't use our same mother as last time. We need to make a new mother function, base 3. Base 3, so it's y equals 3 to the x power. So what's this one? 3 to the negative 2 power. That'll be 1/9. I probably won't graph that one. 3 to the negative 1 power. That's 1/3. Probably won't graph that one either. And basically, the only fraction right now that you can graph in this section is a half. And there might be some exceptions, but for the most part, stick with nice decimals that are graphable, or just stick with the whole numbers, the integers. So 3 to the 0 is 1. The rest of them should be pretty easy. 3 to the 1 is 3. And 3 squared is 9. So this is our mother function. And now we're going to do the vertical shift down 4 units. So we are subtracting 4 from the graph, from all the y values. We're essentially shifting all the y values down 4 units. Let's go through our transformation. I like to give it its name once it's been transformed. It's like it's been born. Now it gets a name. It's no longer the mother function. It's now its own function. I didn't do anything to the x's. So the x's are staying the same x's here. But I'm transforming my y's. I'm not really going to bother with these too much. It's going to be negative 3 2/3. That'd be 3.666666. Probably won't graph that one. And then this one would be negative 3 8/9. So that'd be 8. Again, when you go to graph it, typically don't graph these ones. So we'll graph the nice ones. Okay. And the vertical shift is also the asymptote. So you're going to get a new asymptote at negative 4. This takes a little getting used to because we call it the vertical shift, but it becomes the horizontal asymptote. That's because you're moving the asymptote down 4 units. I need this space to draw my graph. I ordered a nice graphing board on Amazon. Hopefully it comes by next week. So my graphs will look a little nicer next week. It might be more important next week that we get that done. So I'm only going to graph these nice points. So I've got 0 and negative 3. Here's something I want you guys to do. Graph the asymptote first. Horizontal asymptote. That's at negative 4. Graph that first, and then come over here and pick the points. So 0, negative 3, 1 and negative 1, and 2 and 1, 2, 3, 4, 5. I know I'm getting a little sketchy over here, but it's okay. That's why it's called a sketch. That's where we get the word sketchy from, or sketcher. Okay. So there's my sketch. You probably know what I'm going to ask next. Domain, yeah. Free answer. And range. Domain, take your free point. You get negative infinity to infinity. Range. Range depends on the graph. You're looking at the y value. So the y value goes from negative 4, not touching it. So this graph will never touch the negative 4 all the way up to infinity. And so there's your domain and range. Okay. Next example. Example 4. Graph f of x equals negative 4 to the x. Notice the way I said that. I don't say negative 4. Okay? And it's tricky because that looks like negative 4. But this is not really a negative 4. This is negative 1 times positive 4. The base must be positive. Okay. This is like your A, and this is like your C. Yeah, at the beginning of the lesson, I said you have CAX. Well, now we can see our C. Yeah, our C is negative 1, but our base is 4. So when I read this, I say negative, wait for it, 4 to the x power. Because if you say negative 4, you will screw up all the points on the graph, and they'll all end up upside down and backwards and in the wrong place. Okay. So this is the way we do it. We're going to do a base 4 mother. I always start with the same x's. Negative 2, negative 1, 0, 1, and 2. That's not a law, that's not a fact, that's not a theorem or anything, it's just a technique. You know, 2 negatives, 2 positives, and 0. You could certainly modify this and choose different x's. I've tried, and these are the best. So take it from my experience that these ones work the best. Okay. In my opinion, of course. It's an opinion, it's not a mathematical fact. Here's a neat trick. Start from the bottom. You're going to find that the bottom 3 numbers here, the bottom 3 rows are going to be the easiest. What's 4 squared? Well, 16. Yeah. What's 4 to the first? Oh, 4. Yeah. What's 4 to the 0? Oh, 1. Yeah, so these bottom 3 rows, you can do them mentally. You don't even have to waste all this paper here. There, all this whiteboard space here. For the negatives, be a little careful. Negative 1, maybe you want to write that one down. That's 1/4, or 0.25. Yeah. And then for negative 2, it's 1/16. As a decimal, what's 1/16? It's not one of the ones I memorized. 0.625. You probably won't graph that one anyway. Might not even graph a quarter, but we'll see. I might have to get it in there somewhere. All right, now you're going to do your scalar. Yeah. Your scalar is going to multiply by all the y values. Yeah, C is equal to negative 1. So we're going to come over here, and we're going to multiply all of our y values by negative 1. Be careful. Sometimes your brain will be lazy and say, I don't feel like writing parentheses. Well, if you just put a negative 1 without the parentheses, I already know what will happen. Yeah, I've seen it a million times. You're going to subtract. Yeah, you won't even realize it. You'll just be sitting there doing your math, and your brain will kick into autopilot, and you'll start subtracting. So use parentheses or use a dot whenever you're using a scalar. It's also called a reflector. Yeah, from the previous section, if it's negative, it's going to reflect about the x-axis and flip it upside down. Okay, need to go through the trans table. Transformation. Commencing transformation. Another dimension, another dimension. Another dimension. Another dimension. We're becoming something new made out of something old. So I'm multiplying all of my y's by -1. Okay. Now notice there was no vertical shift. Yeah. So that means the horizontal asymptote stays at y = 0. All right. If you don't see any pluses or minuses on the outside of the function, then it is not being moved up and down. And if it's not being moved up and down, it's going to stay fixed. Then that means our asymptote is going to stay at 0. So this graph is kind of strange looking. The entire graph looks like it's underwater or underground. The whole graph is going to live below the x-axis. All right, so you got your asymptote right at the x-axis, and all the points are going to be below. And here's a little trick we do a lot in this type of graphing as we scale our graph. I'm just going to call that 16. Yeah, let me put it on this side so you can read it. I'm going to call that -8. I'm not going to mark everything. I'm just going to mark the important ones. So there's -4 and then -1. Just plot the nice ones. Don't even worry about the decimals on this one. So you've got 0, -1. You've got 1 and -4, and 2 and -16. And there's your graph. Okay. You probably already know what I'm going to ask. Domain and range. The range is from -infinity all the way up to 0. You have to put it in the right order. If you accidentally put this in the wrong order, it'll mark it wrong. You know, I know what you mean. If you were talking on the phone, you say from 0 to -infinity. Sure, you can say that, but you can't write that. You have to write from -infinity to 0. So the range, be very careful. A lot of graphing today, huh? Too bad my graphing board didn't come yet. So we'll do more next week. But how about another example? F of x is 1/2, all raised to the x plus 3 power, minus 6. We got a lot going on here. A lot going on here. The first thing I want to mention is that it's a fractional base. So you have 1/2 to the x power. That is the same as 2 to the negative x power. So it's your choice. When you make your mother table, you can do y equals 1/2 to the x, or you could do y equals 2 to the negative x. either way, both of these tables should give you the exact same values. So these, whenever you have a fractional base, you can choose to not use fractions and just use negative powers. I tried to demonstrate that in 6.1. I'm not sure how clear it came across. I kind of went away from it thinking maybe when you see the graphs, it'll become a little more clear. All right, so let's go ahead and do this. I'll go ahead and show it to you both ways. If you use the fractional base, yeah, -2, well, let me go ahead and do the work. Let me do some scratch work over here. Do some scratch work here. So I've got 1/2 to the -2. That's the same as 1 over 1/2 squared, which is 1 over 1/4, which is 1 times 4 over 1, which is just a fancy way of saying 4. Yeah, so you get 4. How about the next one? -1. 1/2 to the -1. Well, that's 1 over 1/2 to the 1. This is why people oftentimes don't like to do it this way. For some reason, the mind gets all tripped up with fractions and stuff. So you've got 1 over 1/2. Well, 1 over 1/2 is 1 times 2 over 1, which is just 2. If you don't like to do it that way, well, then do it this way. You're going to get the same result. Let me finish this table first. The rest of them we can do without any scratch work. Remember, 0 is a free answer. Anything to the 0 power is 1. 1 is kind of a free answer too. Anything to the 1 power is just itself. So 1/2 to the 1 power is still just a half. Yeah. And then for 2, 1/2 squared is 1/4, or you can put a quarter, 0.25. Yep. So that would be the fractional base way to do it. The way the problem is written as a fractional base, that would be the same values as your mother function, 1/2 to the x. Okay. But you have an alternate form. Instead of doing fractions, you could just do 2 to the -x. And I don't expect you to do it both ways. This is the last time that I'll do it twice. I just want to show you that you have choices. Whether you like it or not, you've got choices. All right. Let's do our scratch work again up here. This time I'm doing 2 to the -x. The light changed. So I've got y equals 2 to the -2. See how much easier that is? It still comes out to be 4 because these are the same function. They better have the same value. But I don't know about you. That seemed a heck of a lot easier than what we just did. Yeah? How about the next one? 2 to the -1. That's just 2 to the 1, which is 2. Again, same y value, but it's a lot easier to calculate it. All right. The rest of these you can do in your head. 2 to the 0 is 1. 2 to the -1 is a half. And 2 to the -2 is 0.25. So all of these y values and x values are identical. So it's your choice as to which one you like to use. You got 2 mothers to choose from. They're identical. They're twins. Now, all of that backstory was just to get my base down. Now I got to do my transformations. So look at your transformations. The exponent is left or right. So which is it in this case? Plus means left, minus means right. So we're going plus, so we're going to go left. Yeah. And then the outside is up or down. Up is positive, down is negative. So we've got a -6, so we're going with down. Pick which one of these mothers you want to transform. It doesn't really matter, just as long as it's correct. So I've got my x and my y. I'm going to go left 3 units. So I'm adding -3 to all my x's. That's left. And then I'm going to go down 6.
Unknown caller.
I'm going to go down 6 units. That's for all the y values. Up and down, go with x. I mean, up and down, go with y. Left and right, go with x. Sorry about the phone call disturbing my lecture. I violated the cardinal rule, which is you should always shut off your phone before class starts. Okay, let's go to the transformation table. And let's go ahead and draw the graph. So I've got -5, -4, -3, -2, -1. Have you noticed that that always happens? I mean, it's not always these exact numbers, but you always get a nice sequence of points. If you don't, then you did something wrong. All right. Now that pattern only exists in the x's. The y's are just going to be whatever they come out to be. -2, -4. I mean, there is a pattern, but it's not quite as recognizable as this one. -5.5 and -5.75. Oh, and then remember, the vertical shift is also the horizontal asymptote. So the horizontal asymptote should be -6. Whatever your vertical shift is over here is also the HA. That's a buy one, get one free. All right, so this is what we're graphing. I probably won't graph 5.75. So x and y axis, most of the graph is going to be down here. I should put my asymptote first. So 1, 2, 3, 4, 5, -6. There's my horizontal asymptote. Okay, what else we got? Let's see, 1, 2, 3, 4, -5. So let's just pick a couple of these points, -5 and -2. And let's pick these two. I'm going to show you how you could do it on the homework. Just pick 2. Just pick 2 points. I mean, you could certainly do more, but it's better just to pick 2 for this one. So I'm going to go with those 2. . And there's your graph. One of the problems with 2 points is it's difficult to see the curve. So if you put in that third point, you can kind of see the curve. Look, right here, -2 and -5.5 would be right about here. Yeah, see? It's about 5.5. So you can kind of see which way it's curving. It's up to you. Once you've got these 2 points laid down, it should be correct at that point. I mean, unless you put the points in the wrong place. Okay, you know what I'm going to ask. I always end with this, domain and range. I'll definitely ask it on the test. So domain is a free answer, -infinity to infinity. The range is from -6 to infinity. The lowest is -6, never touching -6, going all the way up to infinity. It's a lot of graphing, huh? Yeah, it's a whole section of graphing. We'll probably extend this into another part. Let me do one more example, and then we'll wrap this up. Okay, coming up on almost an hour. So. All right, this will be our last one. So let's go ahead and graph y equals 5 times 3 to the x power plus 2. Now, before I do anything, look at the base. The base is going to tell you who your mother function is. And do not multiply the 5 and the 3 and make it 15. All right. The base is 3. The scalar is 5. So that's going to stretch the graph vertically by a factor of 5. There is no horizontal shift. Because there's no pluses or minuses on the x, so there's no horizontal shift. But there is a vertical shift. Vertical shift up 2 units. So it's really important that you read the question carefully so you can kind of prepare yourself mentally for what you're about to do. If you just read and start plugging in numbers and try to graph it, good luck with that. It rarely ever works out in your favor. Okay? So spend more time, thinking about what you're doing before you actually do it. All right, so base 3 table. I'm going to speed things up by just using a previous example. So look back at your notes. This one was 0.88888. This one was what was this? So this was 1/9. This was 1/3. So this was 3333333. Actually, no, this was 0.11111, 1/9. This was 1. This was 3, and this was 9. Now we've already done that. This is y equals 3 to the x done previously. So I already knew all of these y values here. If you don't already know them, then you have to do them all from scratch. Okay. This is 1/9. This is 1/3. This is 1, 3, and 9. Okay. So now we're going to multiply the scalar first. Multiply all the y's by 5. Then we're going to do a vertical shift up 2 units. Be careful, the order matters. If you accidentally switch the order and do the +2 and then the ×5, you're going to get it wrong every time. So you got to multiply the scalar first and then add the 2. Think of it as the order of operations, right? You would multiply before you would add. Yeah? At least I hope you would. Sometimes people don't do the operations in the right order. Since there's no horizontal shift, the x's are not going to change. They're going to stay exactly the same x's. This function doesn't have a name. It's just called y. So it doesn't have a name like f or g. So in that case, I better know that I'm done, because this is now my new y. And these are my old y's. I hate to call the mother function old, but it's the one that came first, so it's old. It's better than calling it used, I guess. You can use a calculator for these if you really want. So you've got 0.111111 times 5 plus 2. So you're going to get 2.555555. 0.333333 times 5 plus 2 is 3.66666666. Okay, you probably won't graph those anyway, but what the heck. It's nice to have them. You should know what they are. Whether you graph them or not is irrelevant. They could really save you if you accidentally start graphing in the wrong direction. These points could tell you, hey, wait a minute, slow down, you're going the wrong way. All right, now these are the values you're actually going to graph. 7, 17, and 47. In the interest of time, I'm going to go ahead and just draw the graph. Remember, your horizontal asymptote is the same as the vertical shift. If I had a graphing board, or if I had a bigger whiteboard, I would probably be a little bit more precise. I'm just going to call this 2. Now, you don't have that luxury. You're going to have a limited space. You're going to have to try to get these to fit. If they don't all fit, pick the 2 that do fit. I'm just going to pick these 2. So 0, 7, and then 1 and 17. I'm going to exaggerate my scale a little bit. So I'm calling this x equals 1, and this is y equals 17. That way I can fit it on my paper. Otherwise, well, maybe I'll make it look a little better. How about like that? There we go. I mean, it should line up with the x value. All right. That's good enough. I mean, that would be just a basic graph with 2 points. That's the bare minimum. 2 points and the horizontal asymptote. Okay, and I always end with the domain and the range, just to make sure you don't forget that. Domain is, of course, free. Take it. Free answer all day long. Range is based on the graph from 2, not including 2, all the way up to infinity. Okay. We're not done. I'm just signing out for the day. We will continue with a part 2 tomorrow. Peace out.